Hey, in this video, students will be able to identify the factors affecting work done by constant forces and power. So in physics, work is defined to be the product of the magnitude of the displacement times the component of the force parallel to the displacement. That's a lot of words for meaning it's force times displacement. That's what we define as work. And this whole parallel stuff means that the force has to be along the same direction as the displacement. In other words, if the force is perpendicular to the displacement, this wouldn't work. They have to be along the same plane or along the same line, basically, like up and down or left and right. Sometimes there might be an angle at which something is pulled, then we'll add cosine theta on. We're only going to add this cosine theta part if there's an angle involved in the problem. So usually it's pretty clear. There'll be like some number of degrees somewhere. So the W stands for work, not weight. A lot of times people get confused and put in weight here. Remember, weight is a force. So weight is Fg, not W. It's measured in joules, and the unit for joule, or the symbol for joules, is capital J. F is force, measured in newtons, like it has been all year. D is displacement, not distance. It's very specific here, measured in meters. And the cosine theta refers to the angle between the directions of the force and the displacement, which I'll show you an example of momentarily. The parallel line things in between the F and the D mean that the force has to be parallel to the displacement. In other words, that's when cosine is zero, like there's no angle between them. Joules, J, is the unit for work and energy. It's the same unit for all of it. And 1 joule is an abbreviation. It stands for a Newton meter, or in other words, a kilogram meter squared per second squared. Instead of writing all that stuff every time we do work, we'll just write joules instead. It's named after a guy named James Prescott Joule, who in the 1800s did a lot of study on types of energy. So physicists named this unit after him, which kind of makes sense. So sometimes we will incorporate this cosine theta part. That would be like if you pulled something up at an angle. If you think of like a suitcase that has wheels and you're dragging the suitcase, you probably have an angle between the floor and your arm. So that's when you would use this, and you would need to plug in this angle there. But the force is still how hard you're pulling it, and the distance is, or the d is the displacement, how far you move it. So if someone runs around a track one time, which is 400 meters, with a force of 10 newtons, how much work is done? If you did 400 times 10 and got 4,000, that's just not right at all. That's terrible. Because the displacement's zero. If you run around the track one time, you didn't actually go anywhere. Your displacement's zero, so the work done is zero. 0 joules of work. In other words, if you end where you start, you didn't do any work. This might be counterintuitive because you're thinking, well, I ran around the track. I definitely expended energy to do that. But in terms of what work is defined as, it's force times displacement, not force times distance. So you can do no work but have expended energy. Some other examples of zero work. If you push on something but it doesn't go anywhere, like say it's too heavy to push and it doesn't move, then you didn't do any work, even though you exerted energy trying to push it. Like if you try to push down a wall, chances are the wall's not going to go anywhere. But you will have felt like you did something, but nothing was displaced. If the force is upward, like in this picture, but you're moving it sideways, technically you're not displacing the object in the same direction as the force. That's where the parallel lines come in. Like you'd have to push it the same direction of the force. So if you were lifting it, there would be some work done here. But just carrying something technically doesn't do any work. On to power. Power is defined as the rate at which work is done. The equation for it is power equals work over time. P stands for power, measured in watts, named after a physicist named James Watt. The W stands for joules of work, and T stands for time in seconds, like it has been all year. So basically, this isn't weight, it's work again. And the idea is that if something does more work in a given time then that's more power. If it takes more time to do something, then that's generally less powerful. This kind of makes sense. If you could do something very quickly, that demonstrates power. If it takes you a long time to do something physical, then that's less power. But also you could do more work or less work. So those both affect how much power output